Hi, in this video I'm helping students in my Statistical Analysis class, Introductory Statistics, at Bethel University do something I call EHW1, which stands for Electronic Homework 1. However, if you're somebody else or from around the world who doesn't go to Bethel, but you think you might get some benefit out of learning how to use spreadsheets to use what are called sum of squares formulas to solve for linear regression problems to find correlations and slopes and intercepts of regression lines, then you might get some benefit out of this video too. So what we've got here is some data from exercise 2.69 in the textbook that we use, at least the 4th edition of that textbook and a future textbook. It might not be that exercise, it might not even be in the book, however I might still assign this assignment. And I'll just show you what the problem itself looks like. You can pause the video if you'd like to read this over, and now I'll talk about it briefly. What we've got here is essentially trying to measure the amount of pollutants, nitrates, in water in different manufacturing plants, or the water near different manufacturing plants. And you've got two quantitative variables here. X is the nitrates, which are measured in milligrams per liter of water, and Y is the absorbance. It doesn't tell you what the absorbance scale is. It's not a big deal. And what we do see here is that you see that as X increases, it seems that Y is increasing as well. So there should be perhaps a strong correlation between these things. It's not necessarily linear. However, we will see it's actually a very strong linear relationship. And that's what we're going to go look at right now. So coming back to the spreadsheet, you've got the data in here. And if I go over to the right here, I've got the graph of this relationship. There we go. X, the nitrate amount, is on the horizontal axis, milligrams per liter of water, and Y, the absorbance, is on the vertical axis. And you can see those points look like, for all you can tell, they are exactly on a straight line. Now, that's actually a bit of an illusion, and actually these 2 points you can see are not. That's a little bit of an illusion. They are not exactly on a straight line. They just look like they are. But it's a very strong linear trend with a positive slope, so you should expect a correlation and a squared correlation very close to +1. In fact, looking up here, the spreadsheet effectively says R squared, the squared correlation, is 1. That is actually an approximation. It's not exactly right. You also see the regression line. It's not written in the standard way. Absorbance Y. There should be an equal sign here, but I couldn't make the spreadsheet put an equal sign here. Y equals 0.113x plus 1.66. The slope is 0.113, and the y-intercept is 1.66. We now want to confirm those things with some formulas and with spreadsheet capabilities. We want to ultimately fill in these cells that you see here, colored in aqua, to find various things that you see here, including what are called SS quantities, standing for sum of squares, and ultimately calculating the correlation coefficient and the slope of the regression line to confirm this regression equation that we see here. Now over here I've used some spreadsheet capabilities to calculate the slope and the intercept in alternative ways, and my students will see that when they look at the formulas up here. The correlation does end up being very close to 1, as you can see here, and its square is also close to 1. Turns out the slope is about, again, 0.113, and the intercept's about 1.66, although it's carrying more decimal places here. So again, your goal is to ultimately fill these in. How? What are we doing here? We're using what are called, again, SS formulas, sum of squares formulas, that I have in this PowerPoint slide here. Let's look closer at them. So we have this thing, SSXX, then we have SSYY, and then we have SSXY. SS again stands for sum of squares, and you see these sigmas, these capital Greek letter sigmas, standing for summations, adding the things that are to the right of them. So we're adding up x minus x bar squared for different x values here. Then we're adding up y minus y bar squared, x bar and y bar being means here of x and y individually. This last one's not really squaring. We're adding up products x minus x bar times y minus y bar, but it's similar enough that we might as well still use the SS notation. So these formulas are the definitions of these SS quantities, and over here on the right we have alternative formulas for those SS quantities. These are the things that we will actually be using in the spreadsheet. Okay? Once you've got these quantities, then you can calculate R, the correlation coefficient, by taking these quantities, SSXY, and dividing by the square root of SSXX times SSYY. And then you can find the slope of the regression line, B1, by doing this division, SSXY divided by SSXX. Now you might be saying, well, do I really need to learn these things? And it's true that it's not the most important thing to get out of a stats course because you've got the technology. These were useful formulas back before calculators and computers came along. These were the most efficient ways to calculate these quantities, say before 1950 or so. Okay, so they're not really used so much these days. However, I think they're still worth learning for a couple reasons. One is you may see them in a textbook in the future, and you know, if I didn't introduce them to you now, you might look at them and say, oh, this is really scary looking. And it still could be scary looking, but at least you'd say, I've seen those things before, I learned about those, I practice using them a little bit, and it might make it a little less scary in the future. Another reason to learn them is that it's just good practice with spreadsheets. And besides practicing the spreadsheets, I am going to emphasize a few other things in the video here too. So it's worth doing, I think, as an electronic homework assignment. So let me show you these things again. You may want to pause the video and write these down if you don't have easy access to them, because now we're about to go ahead and use them in the spreadsheet. And I'm going to assume that you've seen them and know them or have them in front of you. So again, you've got the data here in these different cells. You've got various things that can be calculated, sums of these columns, sums of the x's, sums of the y's. I could use a sigma notation here symbolically to represent those sums. You've got means, average of those things, of the x's and y's using formulas that like equals average that you see here. My point is not to show you how to calculate these things. My point is to fill in what you see over here and confirm those numbers. And again, when you're doing this, if you're my student, you should really be thinking about this as a learning experience where you're writing down on paper perhaps what I did, you're taking notes, and then you should practice doing these things on your own. I may test you on them in the future. You may need to use them in a project, for example. So you want to learn. That's the goal here. So write things down and then practice it on your own and check and see that you get the right answers at the end. All right, so what do we do to start filling these things in? We need to use formulas. Here, this column you can see is labeled x squared values, and this column is labeled x. The nitrates, those are the x values in milligrams per liter of water. We want to square those numbers and put them in column D here. Now, of course, I could just do, well, first of all, I need an equal sign if I want it to do math. That's the signal to the spreadsheet, in this case Google Sheets, to do math. It's the same in Excel, for example. I could type equals 50 squared, like this. However, it's going to be more beneficial to use a formula, to use the cell reference for where that 50 is. It's in cell B6, column B, row 6. So it's best to type equals B6 squared like that. Okay? And the great thing about the formula is it's copy and pasteable. I can copy and paste the formula down by either you doing a copy and paste or just clicking and dragging the lower right corner, and it's going to correctly square all the numbers in this column. For example, 100 squared is 10,000. 200 squared is 40,000. 400 squared is 16,000. Okay? And the formula up here in the formula bar did get updated correctly. That's what I wanted to do. Okay? I can also now copy and paste those formulas into column E, and it will correctly score the y values. So the C's will get the B's will get updated to C's by copying and pasting this to the right. It will now square the y values. For example, 7 squared is 49, 24 squared is 576. You can check these things with your calculator. And if you look at the formula here, you see, for example, here an equals C9 squared. I never typed that. You know, I only typed an equals B6 squared up here and copied and pasted. But things got updated correctly. I can't do the copy and paste into this column because it's a different kind of calculation. It's not x squared or y squared values. It's x times y values. So I need a different formula. And by the way, you don't have to type the formulas. You can click on the appropriate cells, although of course I'm doing a little bit of typing. Equals B6 times C6, that will calculate 50 times 7 and be a correctly copy and pastable formula downward. Okay, so now again click and drag this down, and then for example you can check with your calculator that 2,000 times 226 is 45,200. Alright, what's our goal now here? I'm going to go downward now. I will fill in the stuff to the right here that you see, but this is something different. It's unrelated to the sum of squares formulas that I showed you, though there is still an SS there as well. I want to fill in stuff that you see down here that's in the aqua color. These three things here and these 5 cells here. These 3 cells I want to find by adding up, by summing these columns. Now I've actually done sums in these columns, B17 and C17 I've done equals sum to add up those columns. However, I would like you, for the grader's sake if nothing else, to keep the color the same, and if I just copy and paste that formula over there, the color will change. I mean, of course I could re-click the fill color here, but let's just go ahead and type equals sum equals SUM. We'll add up the numbers in this column. Is what I want. Column D, going from D6 down to D15. I could highlight those cells. I can also just type D6 colon D15. The colon means go from D6 all the way down to D15. So this is it's more than a formula. You could say it's a function, the sum function, where it's something that's taking this column as input and giving you the sum, what I get when I add those numbers as output. SUM. There it is. 100 what would that be? That's 12,855,000. Now I can copy and paste this formula to these 2 cells to add up those columns, and the fill color should stay the same here. So I'm copying and pasting those over there, and you might want to take your calculator and just double check these things. Okay, add up those numbers, see that you get these 2 things. Okay. But now I want to illustrate those SS formulas. Maybe I should just show you them once more. If you didn't get a chance to write these down, go ahead and write them down now. Pause the video, okay, because I'm about to use these now. So coming back again to the spreadsheet, first thing I want to calculate is SSXX, the formula for the sum of squares of x minus x bar squared. And I want to use that shortcut formula that was further on the right on the PowerPoint. So based on that formula, the first thing I want to do is I want to compute the sum of x squareds. Okay, I already have that number. I've already computed it. It's the sum of this column. It's in cell D17 right here. So I'll just click on that. That's the sum of the x squareds. Okay, maybe I should show you right here. It's this thing right there. Then I'm going to subtract the sum of the x's quantity squared divided by n, where n is the number of data points. I guess I didn't use a built-in formula to calculate the data points, so I'll just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Okay, I will use the fact that n is 10 here. I want to subtract now the sum of the x's, which is right here, quantity squared divided by n, which is 10. I'll just type it in as a 10. This should be this quantity SSXX, excuse me. Double check it with the formula over further on the right here. That's what I just essentially did. Adding up the x squareds gives you this number. Subtracting the sum of the x's quantity squared gives you B17 quantity squared. Divide by 10 because n is 10. There were 10 data points here. This should be SSXX. Now, why is that not entering? Come on, enter. There we go. Now I can't copy and paste that formula for SSYY and SSXY because the formulas are different. I'm going to use different cell references for these things, but they're similar. Look quick here. I'm going to do this formula next. So I need the sum of the y squareds equals, why is this stalling on me? There we go. Equals sum of y squareds. The y squared values are here. The sum is in cell E17. So let's go ahead and click there. Minus the sum of the y's quantity squared divided by 10. And by the way, the spreadsheet does know how to do order of operations correctly here. If you were trying this by hand with calculator help, you'd want to do the square first and then divide by 10 before subtracting it from this. Okay? And the spreadsheet knows to do this. You should, if you check this by hand with a calculator help, get the same answers. And then the sum of the SSXY, I need this number, minus, not something squared, it's the product of these 2 things, sum of the x's times the sum of the y's divided by n. Okay? These are the numbers that you should get. Now let's go on to the correlation and the slope with the formulas that are at the bottom of this. Look at those. All right, here we go. We're going to use those. The correlation is SSXY, use the numbers we just found, divided by the square root, SQRT is square root. You can also raise to the half power of this times this, And when we enter this, and you can actually already see the answer here, we should get a match to this thing over here, 0.999939231.8, and that is indeed what we get. We have a match. You can check your work. Okay? And the slope, we use the other formula, SSXY divided by SSXX. Again, use the numbers we just found, SSXY. It's right there, divided by SSXX. Right there, and this gives you the right answer for the slope. 0.113010864 matches the slope that's there. Okay? So that is going over the SS formulas. Now we want to continue and do something else. Now this is something different. We want to calculate these quantities that you see up here, y hat, predicted absorbances that come from the regression equation, residuals or errors that you get from that, and squared residuals. Then we want to add those up to find something called SSE, which stands for sum of squares of errors. Error doesn't mean you've made a math mistake. It means you've made an error in your prediction. Y hat is perhaps slightly different from Y in this case. That's where the word error comes from. Probably a residual is a better word so that that confusion doesn't happen. But SSE stands for sum of squares of errors, sum of squares of residuals. That's the final thing we will compute. And the main conceptual point to make about this, besides some spreadsheet points that I'm going to make, is that SSE is minimized. It's as small as possible when we use the slope and the intercept of the true regression line that we see. I guess I'll use these numbers that you see there in cells B23 and B24. Okay? So it's going to be minimized when I use those quantities. If I used a different slope and a different intercept, we'd get a bigger quantity for SSE. Okay? Now you could test that out on your own, but of course my students, you're going to want to turn it in with the right number in there. It's going to be as small as possible, and that's why linear regression is sometimes called least squares linear regression, because we are minimizing, making as small as possible, as the least as possible, SSE, based on, again, the slope and the intercept of the regression line. But how do you find y hat, the predicted absorbances? We use the regression line and we use the x values. So here's the equation. The equation of the regression line is here. I could use and let me also illustrate another feature of spreadsheets, fixed cell references. Now I did not use fixed cell references for here because I wanted the cell references, the B6, the B7, the B8, etc., to get updated correctly. But when I use the slope and the intercept that come from cells B23 and B24, I want to use those cell references to say fixed as I copy and paste the formula downward. There is a way you can make those fixed. Again, they come from B23 and B24. Here's how to do it. I want to take the slope, which is in B23, and multiply it times B6. If I use $B$23 times B6 without dollar signs, the dollar signs do not refer to money. They refer to fixed cell references. And then I want to add $B$24. Technically speaking, the dollar in front of the B fixes the column, and the dollar in front of the 23 fixes the row. However, for most applications, if you sort of want to play it safe and don't want to have to think about it, do I want to fix the row or the column, you can just fix both the row and the column and use both dollar signs. That is going to take that slope from cell B23, and as I copy and paste the formula down, it'll keep it at B23. Notice there's no dollar signs with the B6. I want the x value to get updated from B6 to B7 to B8 as I copy and paste downward. I do have dollar signs with the B24 where the intercept was. I want that to stay the same. So the dollar signs don't mean money here, they mean fixed cell references. And this will give me correct y hat values based on that. And you can double check, click on one of these cells and look at this formula bar here, for example, and you can see it down here. The B23 and B24 stayed the same, but the B6 got changed to a B11. So again, what I'm doing here is I'm really plugging the x values into the regression equation, the slope times x plus the intercept, to get y hat values, predicted values. And you can notice, because the correlation is so close to 1 here, that these y hat values are in fact very close to the corresponding y values on a relative scale at least. Okay? These numbers, relatively speaking, are pretty close to these numbers. It's a strong correlation, a strong linear trend here. What are the residuals in these y hat values? The residuals are y minus y hat. So I want to take the y values over here in column C and subtract the corresponding y hat values from column G. And as a copy and paste, I want those to get updated all the time, so I do not want to use dollar signs, do not want to use the fixed cell reference operator. Here I'd type equals C6 minus G6 to take the y values minus the y hat value. You can see this one's going to be negative. That's because the y hat value is bigger than the y. So when you do y minus y hat, you get a negative number. When y hat is too big, then you get a negative residual. When y hat is too small, you get a positive residual like this one. This y hat value is a little smaller than this y value. Okay? Here we have two data points here with the same x value but different y values. That happens down here as well, which was actually easier to see in the graph. That does lead, since the x values are the same, that does lead to the same y hat values, but it does lead to different residuals because, again, the y values are different. So these are the residuals that you should get. Now I can square those things. Equals h6 squared. We'll take the number in h6 and square it. Of course, when you square a number, whether it's positive or negative, you will get a non-negative number. These are all not going to be negative. They will be greater than or equal to 0. I can copy and paste that formula down. There's the squared residuals, and now I can just add those up with either equal sum, or I can copy and paste from over here. That's the sum of the squares of the errors that you should get, 9.048. If I now went back, I won't do it, but if I did go back and changed the slope and the intercept that I used from the regression equation, even a little bit, SSE would get bigger because this is as small as it can possibly be. The slope and intercept of the regression line minimize the sum of the squares of the errors, the sum of the squares of the residuals, and that's why it's called least squares linear regression. So I hope you'll learn some things about both regression and using spreadsheets, and that is my goal with my students. Thanks for listening.